Okay, hello everybody. Welcome to Reflections on Supply Chain Trust, the software factory. We are going to talk about supply chain, which of course is the attack du jour, and run through a couple of live demos as well to give some concrete implementation and terrorification of the supply chain's inherent danger. I'm Andy, I'm CEO at ControlPlan, where we do cloud-native security engineering, threat modeling, and penetration testing. I have done a little bit of everything. I have a developer background. I have a care for the operational concerns of people at runtime. How do our systems work when the rubber hits the road? And of course, I have a deep and inherent interest in security. I'm very fortunate to have been given the opportunity to write Sec 584 for O'Reilly, for SANS, that is, attacking and defending containers and Kubernetes, and I'm a trainer for various places. I've just written a book, which is now available. Should you wish to read it on O'Reilly online, I have a discount code that'll get you 30-day access, which is probably a sufficient amount of time to read the book. See, I'm very slightly off the bottom of the screen. Let me see if I can fix that. Maybe that's better, maybe that's worse. Yeah, it looks like it's still bleeding off slightly. Okay, there we go. There's nothing super important there. And I will release the slides afterwards as well. So we're going to talk about the supply chain. What is it? Why does it matter? Then we'll look at how to attack a supply chain. Concretely, the steps we can take to compromise our own or somebody else's infrastructure. We'll look at signing approaches, which are the mechanism by which we ensure that each individual stage of the build that we control, or indeed the upstream producer that we're looking to consume, is validated for some level of validation, for some degree of trust. And then finally, the software factory approach. This is a mechanism that ties everything together and hopefully brings us to a slightly safer place compared to where we have traditionally been as an industry. This was all over KubeCon last week. There are so many good talks there. This is a high-level summary and a joining together of disparate parts. I strongly recommend that you go back, if this is your area of interest, and examine not only KubeCon, but Supply Chain Security Con, which was a day zero event and full of luminaries giving their best, and some excellent slides. I think the talks are online in 2 weeks. So what is a supply chain? Well, first of all, it is the current matter of conversation in many security departments. It is anything that we inherently rely upon. So in a military context, these are the nuts and bolts that have a SKU that go into your aircraft carriers, the entire end-to-end chain. It's how the CPUs are manufactured for bits of the computing on board. In a pharmaceutical context, it's making sure that when we give drugs to people, they are exactly of the composition that we require and don't have any impurities or things that would negatively affect the outcome for humans, for individuals. It's the same from a food perspective. We've seen different kinds of supply chain compromise, even things as simple as people putting needles into packets of strawberries a few years ago in Australia. Manufacturing, of course, is our Toyota style last minute, and software, the thing we care about the most, and that we shall be talking about in the most detail. The important thing here is the producer-consumer relationship. As a consumer, we inherently trust everything that is provided to us in the supply chain. This is problematic because that producer is also a consumer of somebody else's product. All the way down, the turtles continue. And in this case, we are reliant upon trust, which is potentially the area that we find ourselves compromised the most. So a software supply chain is anything that is running in production and anything that we ingest and use in order to deploy and achieve the ultimate goal of creating business value for our stakeholders and employers. What could possibly go wrong? Well, it's a great question. We have to trust everybody upstream. And things can go catastrophically wrong without us necessarily being aware of them. So in this day and age, everything is software. We begin with the applications. We know that they're made of software because that's how it's always been. But infrastructure now is programmable. We can define how software works and how the infrastructure is built purely with declarative formats like Terraform, with CloudFormation and all the various permutations of those things. But that's relatively well known. We're now into a security and policy as code space where we look at tooling like Open Policy Agent that allows us to define our own complex policy in order to enhance the security or the safety that we perceive in our systems. If we push everything through the same kinds of pipeline, we can get some advantages by treating everything as software. For example, everything can be packaged into an OCI image. If our build chain runs static analysis, it runs linting on those individual parts. So everything, for example, is YAML or JSON flavored these days. We can find some commonality between the different types of testing that we apply, and we can save ourselves some mistakes. This means applying software engineering rigor to other departments, infrastructure, security, and paying attention to the lessons that we've learned over the past 20 years from migrating our practices from a kind of general anything goes into our types of testing, our build processes, and caring about quality and assuring that in a provable way. There are many different types of pipeline for the purposes of this conversation. It's everything. We want our build servers, which are essentially remote code execution as a service, to do the thing for the developer. So the developer no longer has to build, compile, package, sign, and distribute. Instead, we just commit, and the build server does that work for us. From an infrastructure perspective, when we have the keys to deploy things into a cloud provider, that is desirable for an attacker. And of course, the reason for that is that infrastructure can be turned into sweet cryptocurrency if we allow, or if we don't control where those keys end up. So segregating application and infrastructure pipelines is probably a sensible thing in the first place. For security and non-functional requirements, well, then we're talking potentially if we're looking, for example, to rotate all of the certificates across all of the devices in our estate, we would want perhaps a management network to do that. We would want those keys to be so restricted. You can pwn most organizations by getting into an SRE team member's laptop somehow. So this is the level of concern that we have. This is expensive, it's difficult, it's computationally heavy, and at the moment, unfortunately, this is the remit of regulated industries or those for which this kind of breach becomes an existential crisis. We hope to commoditize and make this easier, and this is the point of the software factory. So the supply chain, everything is composed of software, even software itself, down to some original thing. There's a huge amount of complexity in securely bootstrapping a build system. Again, we'll get into this later. We rely on other people's software. The supply chain is long and difficult, and we want correct and non-violent code to be delivered to us by our producers. This reliance is a difficult thing to prove. In this hypothetical supply chain with Alice, Bob, and Charlie, if Bob, as the intermediate step in that three-step system, drops an implant or changes source code in a malicious way, well, suddenly malware is running in production. If that provider, Bob in this case, is, for example, SolarWinds, then we've seen the network effects. And this is why supply chains are so difficult to secure, because when we are installing highly privileged software onto a multitude of servers, and again, in the SolarWinds case, one individual producer has hundreds of highly regulated and, as we saw, often classified consumers, that single attack amplifies dramatically by virtue of the number of organizations that trust the producer. So they are long and difficult to secure. We have to trust everything, and they are the new security frontier since about 40 years ago, thanks to the seminal paper, Reflections on Trusting Trust, where Ken Thompson built a compiler that would compile a malware or compile malicious code into its output. And we've seen this happen again. It's been hypothetical for a long time. It's not necessarily the compiler attack that we deal with these days, but we have unfortunately reached the reality that Ken wrote about all those years ago. So let's look at how we attack a supply chain. The Hacking Kubernetes book features an archetypal 8-bit adversary. I introduced Captain Hashjack to you. His goal is to run his code in your production systems. Why does he want to do that? Because that's where the big, expensive infrastructure lies, and that is where the juicy, personally identifying or classified or in some way business value derivative data sits. Production is what we want to defend. And we have seen plenty of instances of supply chain attacks over the years. Very recently, we saw the Revil ransomware kicking the Colonial Pipeline offline. That attack was actually on a supplier for that organization. And so once the supplier is infected, then privileged access from that supplier was exploited to attack its own consumers. We saw SolarWinds, which again is this highly privileged security and monitoring agent that's installed on many government systems. The nature of this attack was a nation state adversary getting access to the build systems and at the point of compilation, switching out a specific source file. That source file essentially embedded the Cobalt Strike command and control server. And because the compiler trusts what it's given and the signing authority signs whatever the compiler gives it, by impacting the supply chain directly before the moment of compilation, we end up with a signed, trusted artifact that's then distributed and installed without raising any eyebrows. In fact, the nature of the command and control traffic went over DNS and it looked like a legitimate set of domains. It vaguely imitated the style of SolarWinds traffic. So it was incredibly difficult to detect. As we saw, FireEye, who are kind of top of their game, were needed to self-identify their own systems, vulnerabilities, and compromise in order to educate the rest of us that, in fact, there was a problem. Code coverage and homebrew, both slightly different types. Code coverage was actually a CI/CD attack where there was a leak of credentials that allowed somebody to implant their own monitoring agent. So people in their build systems would just download this compromised agent, install it, and then again, CI/CD is remote code execution as a service. It has to be fully trusted because we are offloading work from the developer. If the developer was previously signing and packaging and pushing things to production, well, those highly privileged keys and credentials must exist somewhere. In this case, they existed in the build system, and this compromise leaked the probably AWS keys, again, of hundreds of organizations. A couple more in here, but the most notable at the end is Xcode Ghost, which was a backdoored version of Xcode available on the BitTorrent and sort of Wares sites to blast from the past. Once people downloaded that and compiled their own iOS applications, again, a command and control server was inserted into those applications. So somebody legitimately building and publishing to the App Store is accidentally distributing malware because of this compromised compiler. As you can see, there are a huge range of different types of supply chain compromise. We can go in straight for the source code. And in fact, this list comes from Tag Security, who are doing the honest security work to keep us safe. They are a subset of the CNCF, and they're the technical advisory group. And they maintain this list of supply chain compromises. So notable compromises are available and categorized. As we can see, in many cases, it's just a case of putting malicious code into the source. This could be done by exfiltrating SSH keys from a developer's laptop. It could be done by writing directly into a compromised self-hosted Bitbucket or GitHub Enterprise or whatever your self-hosted Git tooling is. There is a caveat here, which is, of course, if we're writing into a Merkle tree and we've got sensible branch protection, that source code compromise will last in perpetuity. We'll know that it happened. We can do relatively easy attribution. I say attribution, but at least discovery, because it's there and it's encoded into the Git Merkle tree. We can't force push over it. More insidious then is dev tooling. If we can get into something that runs as part of our build, then we're looking at modifying the source code as it's in flight, as it's about to be compiled, as it's about to create that final artifact. It's far more difficult to detect because, again, our internal trust is such that we don't expect our developer tooling to be compromised. Publishing infrastructure, again, it's the same kind of style, but instead of impacting the tooling, it's compromise of the build server itself. Perhaps it's compromising the operating system packages that are running in the container that's doing the build. Trust and signing says that, okay, we don't care about anything before. Instead, we're just going to build malicious packages and then sign them ourselves, switching them out for, or making them available to people in a kind of watering hole attack where we imitate a trusted party, but in fact, we're giving untrusted code, but it's trusted because that signature says it's so. And then the last two, attack chaining, is a superset of any of the previous, and negligence is things like committing our keys to GitHub. Fortunately, we now have a lot of companies who are scanning all the open source or public commits on GitHub and will notify not only the relevant developer, but in some cases, they will terminate the keys at AWS, for example. That story, at least, is getting better. So what can we do in a supply chain itself? We can go for the developer's machine, and I'll demo how easy this is shortly. There's a question here about signing. A GPG signature says, or in fact, any signature says, at the point in time that this signature was made, the owner of this key had some level of trust in the thing. Time, person, abstract trust, entity. It doesn't mean any more than that. And there's a philosophical debate here about how much we should sign. From a Linux kernel perspective, Linus suggests that only the merge commit is important to sign because everything before that is inherently trusted by the merge commit. You may rebase or just come in with a single commit. In my mind, that is appropriate for a system or a development flow that takes weeks, months, or years to merge patches. For open source, it's my personal preference that every commit is signed because not only does it show that level of trust, which is kind of inherent in the first place, but secondarily, it shows that the person had access to a second factor device. If your GPG keys are stored on your host, they can be exfiltrated along with your SSH keys. If someone's got access to your host at that level, they can probably also drop a keylogger on, and so the password lacks much value. So a second factor device that you plug in, maybe make physical contact with, provides an extra level of certainty that the person with the trust at the time is genuinely the person that owned the key. Because of course, if we can exfiltrate that key, we can imitate that trust. We've spoken about the other two, source and build. We can go upstream. We can infect a trusted supplier. Again, these are just versions of the same kind of attacks, or we can go for the runtime environment the source code is in. Compromising an operating system package repository is more difficult, and that's because they already use some of the more advanced techniques that we'll look at here. It's not completely impossible, and of course, it's far more likely when we're talking about dependencies that are not pulled and signed directly by a managing authority, such as Debian or Arch Linux or Red Hat. There is a new framework for this. It's called SALSA, and it's supply chain security something that I can't recall. This broadly is all the things that could go wrong just in the process of building a package. First of all, we have the code review. It's recommended to have either 4 eyes or pair programming. I think the consensus now is that even if we're pair programming, a different pair must merge that commit. This gives us some certainty that if we do have malicious insiders in our organization, it's difficult for them to collude in such a way, or in fact, if they do, and Risky Business, the preeminent security podcast, suggested at one point that 1 in every 40,000 developers is a nation state actor. I think maybe that ratio is even a bit high. It could be lower. So if we have a couple in an organization, they're required to collude to merge something if you can't merge your own pull requests. And again, once something goes into Git, there is an evidential historical record that we can use in root cause analysis and post-mortem. But let's assume that we have we've passed the code review properly, we're into the source, we can compromise the source control system. Again, we can be slightly more insidious here again by modifying the code after source control. That can either be as the build is occurring, which is similar to the compromised build platform. Or of course, if we own a Git server, we don't have to serve what's in the Git repository itself. We can add something on top. We can now pad, and not that this is, I'm sometimes self-conscious that I suggest things that are not yet attacks, but hypothetically, we've seen the shattered attacks against SHA-1. Git is moving to SHA-256, but it's going to take a long time. So it's theoretically possible to pad a commit to fake the head of the Merkle tree, to fake that SHA-1 signature, and you're essentially just putting junk on the end of the commit until such time as the collision attack works. We're looking at a lot of infrastructure, but it's now within the realms of rentable compute. So yes, there are still attacks. Again, that one's slightly hypothetical, but there's nothing to say that Git has to give you what you demand. Onto the compromised build platform, using a bad dependency. So now we're talking about the entire open source ecosystem. This is something that we don't go into in much depth in this talk, but third-party code risk is essentially saying, we love open source. It makes our developers faster. It saves us time on bugs. It allows us to contribute to the greater good instead of having to rebuild everything ourselves. But it also opens up a new frontier. The pull request suddenly becomes a security boundary, because if somebody can sneak code, and especially in more easy to obfuscate languages like C, someone could sneak potentially benign looking code that has negative side effects into that dependency tree. Again, we are potentially going to run that in production. And it doesn't have to be a backdoor. It could be something that allows further compromise. It could be something that allows further compromise, like weakened random number generators, or something that allows privilege escalation with a crafted exploit that no one else is aware of at that point. Of course, it can be plenty more things, just like firing off a reverse shell, or by dumping the environment and pushing that to GitHub. Having restricted firewalling to places that we pull dependencies doesn't mean that somebody can't put signing keys, publishing keys into their attack and use GitHub or the Docker Hub or NPM or any of these things as command and control, because as soon as you can write there, you've got an effective way of getting that out. There was a great demo of DNS exfiltration from Ian Coldwater and Brad Giesemann at KubeCon. Of course, again, it's super difficult. How do you fix that? Well, you have to run split horizon DNS and prevent those recursive lookups going to the internet. It is such a level of complexity that most places will not do these things. The difficulty then is we need to stop the supply chain being compromised rather than looking to try and band-aid the side effects, because both are expensive, but actually production constraints can have far more impactful concerns for our operations teams, who then have to operate in a straitjacket. On we go then to bypass CI/CD. Well, fine. Let's just package our malicious code and push it straight to our dependency, our internal repository. We could compromise that repository in and of itself. So the source code's fine, all the provenance all the way through, but if the code at rest before it goes to production is compromised, again, what do we do? And finally, been embarrassingly long on this slide, it seems, using a bad package, something that's sort of escaped its way through these things in one way or another. So let's demo the first of these. So what we'll do is we'll take a malicious NPM package. So this might be something I built myself. I mean, in this case, it actually is. And what we'll do here is we'll install, let's do this a bit smaller. So we'll install a package locally, but we'll emulate what's happening when we install directly from the internet. So we've got a package JSON. As you can see, we have this marvelous pre-install hook. This allows us to run arbitrary code contained within the same package at the point of installation. So what does that mean concretely? It means an npm install pulls the package, unpacks it into a local directory, and then runs this pre-install hook prior to actually making the thing available for us. This is not published on npm because they would remove it, I'm sure, but we can do an npm local install. So we're going to run this hook, and now it's running my magic keylogger. I'm going to get a Monero miner in there. Then I've dumped the contents of all my local authorization credentials, my SSH directory, truncated for my own safety, but you can see my GPG, cloud provider credentials at this point. Of course, again, operations teams, developers generally have access. It's my preferred pattern that developers have their own segregated infrastructure so they can operate more quickly in a production-like environment. That opens this attack surface. And we can see how easy that was to gather that data, exfiltrate it, all from a compromised NPM package. How might we perform that compromise? Well, there's this wonderful technique called typo squatting, which says if I've got something which is entitled event-stream, as an attacker, I might then register event stream without the hyphen. I duplicate the same official event stream code. I get a notification when they publish a new update, and I just duplicate it into my event hyphenless stream package. And any developer who's manually installing that package is able then to run as they'd expect. Once my malicious package has 100,000 weekly downloads, I put a backdoor in, and boom, I can run this software with that ease. It's taken a long time for this attack to be taken seriously. NPM specifically, because they are the forefront of these highly decomposed functional packages in a far sort of greater magnitude than Maven, for example, which focuses, and Golang, which focuses on much bigger libraries. They now attempt to look at the differences in the strings and identify if there is a potential typo squatting attack going on. It's tricky, as you can see, and the problem again in the supply chain is that any of these points being a point of compromise impact the entire downstream chain. How do we fix these things? Well, potentially we use signing keys and SSH, avoiding plain text credentials so they're not resident on our file systems. Crypto wallets at the moment are most of where these attacks have been targeted, which is a blessing in one way, because if we look at some of the some of those wide network attacks, if they'd been stealing identities, then we would have had, and perhaps like an automated compromise on the back of that, we would then potentially have hundreds of thousands of packages that may be compromised. I'll always fly a small flag for air-gapped developments, even in cloud environments, because they do provide a huge amount of safety from some of these things. But as we've seen, even DNS, it's always DNS, is problematic. Okay, so that was a slightly benign example. We'll now go for a backdoor in production example using Kubernetes. The premise here is that I've managed to make you run my malicious code in your production environment. So what could that look like? Well, in this case, I'm a script kiddie with Kali Linux running. If anything, any proof of concept or exploit that's published on public internet, it's minimum viable security to ensure that our systems are not vulnerable. And we can fix that with things like image scanning that we'll look at briefly. So if I can get you to run my malicious image, and that image fires off a reverse shell, I'm then sat with a public socket waiting for a reverse shell to hit, and that public socket's on the internet, but it routes through to my local machine. All of a sudden, I then have shell access inside your container running in production. If that is just a normal web application, well, hopefully we're fine, and hopefully we've used network policy, and we've got least privilege, and we've delineated our namespaces so that we can't just, for example, compromise a back-end data store by virtue of a front-end attack. And literally what that means is if your web service is running SQL queries, then you can probably dump the database with a remote code execution, or indeed what we're doing here. But if this compromise happens to, for example, an operator that's highly privileged for some entity either inside the cluster or some cloud provider entity, or it has a workload identity that has an even wider attack surface, well, then potentially it's not just a node compromise, it's not just a container compromise, it might be a node compromise, the cluster, or in the worst case, the entire cloud account. And at that point, of course, we can just go and image all the nodes to take whatever secrets are there. We can also spin up our own crypto mining, but probably the worst thing is unfettered access to your organization's data. So what are we going to do here? Now, in this case, I'm cheating slightly because I have access to a Kubernetes cluster right now. And so instead of sort of circuitously, and again, I don't want to put this in a public registry, let's do this in a backdoor manner. So first of all, I'll run ngrok, which is a network grok. It's a TCP forwarder. So it gives me a port on the public internet. And you can see, okay, that's now, so here I'm running ncats locally, which is this command. So I've just got a local listener, and that is forwarded through to a port on the public internet at the point that I run this sizable one-liner. This will. So it runs a reverse shell. We're actually going to do it in YAML and then make it more privileged for the sake of the demo. It doesn't matter that this is the hack image, actually, because we pass a command string to it, which is the standard bash-based reverse shell. Something notable about bash is it creates this virtual dev TCP file system endpoint. This is why you shouldn't put bash in your containers, because we can use this, as you can see, to make a network connection and to essentially bind external commands from that network connection to be piped back through into bash itself. We put this in a loop in case things break, and it will always keep on trying to reconnect. And for the sake of the demo, we are going to turn host PID on, and privileged is now true. We'll tee this the standard error so we can see what's happening, and then apply the thing. Let's see how we go. There we go. So we've created the deployment, and I've now got reverse shell. So we can see root at reverse shell. And just to remind you exactly what's happened here, we've created this deployment 13 seconds ago. That's running inside GKE infrastructure. This is the malicious container image that I've pushed, and I've now got a shell from my local machine into that container. So what can we do here? Well, what I like to do is have a look inside the container. We can see various things. It's leaked its abstraction. We know it's running containerd because of the overlay reports. We can check the disk that's free. Again, another joyously leaky abstraction. etc host is mounted by this particular container runtime onto the host disk. Let's see if we are actually privileged. Well, dev is unmasked. Normally, we would expect a container to not show us anything here, frankly. We can see all the disks that are attached to the host. This is just by virtue of being privileged. But also, if we do a PS, we can see from within the container daemon running on the host. Now, this is just a product of running a privileged and host PID shared container, but it means that we can break out in one of two ways. We can either mount the device. Let's just do this again. So we can mount this device into a mount point, and then we see the host disk in here. And we've also got the, he says, I haven't actually tested this in this demo, but for the sake of it, this is, maybe I'll just stick the whole thing in. This is Duffy Cooley's, again, Duffy and Ian Coldwater's canonical container breakout. NS enter is namespace enter. And here we're going to try and enter the mount, the universal, Unix time sharing, inter-process communication, network, and PID. As I say, I haven't tested this, and on GKE, they harden a number of things. So not 100% convinced it's going to work, but let's try. Yeah, there we go. Cool. So we've now entered the host namespace. It's not so obvious here, but it is obvious from the disks. Let's look at those, because that's not what we saw from inside the container. If you recall, inside the container, we just saw things like etc hosts mounted on dev SDA1. Here we've got everything. So the caveat here is that the demo involved compromising a running, a security context loosened container, let's say. But these are the kind of impacts that can occur just with simplistically getting remote code execution into a victim Kubernetes cluster. So there we go. What are the fixes here? Well, we have to run, again, minimum viable security is scanning our images. This is an absolute necessity. We can't ship 0 days to production. We can run intrusion detection. There is no ultimate last line of defense that matches intrusion detection. We can do anything that we like, but everything is fallible. All computers are broken. And really, without running IDS, we run the risk that we can't detect when one of these things happen. There are some more advanced build time behavioral analytics that we can perform. So this involves essentially a malware lab. It's more difficult. What period of time do we want to wait to see how long the Easter egg might take to blow up? Is it 7, 12, 30 days? Whatever it is, it will slightly decrease our risk of running the application. eBPF is our friend here. There are kernel introspection hooks that run asynchronously that we can use to identify malicious behaviors. And some of those behaviors could include pulling down bytecode, sticking it into non-executable memory, and then marking it as executable. Again, it's an insidious type of attack. It's difficult to spot. Some IDS won't get that in the first place. But really, our first line of defense is the pod security context and capabilities. These are difficult to derive, but the effort is necessary. Containers give us a potentially more secure advantage by offering a higher fidelity of policy. So we can hang far tighter controls around a single process per container than we can with a VM. But unless we apply the security policy and capability drops that go with it, it becomes impractical. It makes no sense, because if we don't apply those, we're just running containers which are close-ish to running on the host. Do we trust the build machines? Okay, let's talk a little bit more about how we fix these problems. Signing is easy. Verification is hard. In this case, this is relatively generic, but what we see here in the middle with the artifact and the provenance record is that we generate metadata about our build artifact, and then we revalidate it at deployment time. This is admission control. This is the hidden superpower in Kubernetes authorization and authentication. It's that third stage, and it's kind of deep packet inspection for requests. It gets the raw JSON payload of the inbound request, and it allows us to statically analyze it or to pull information from other systems that correlates to keys and values that are in there to make admission decisions. There was an awesome demo of an end-to-end version of this at Supply Chain Security Con from my friends and colleagues at Citibank, Michael Lieberman and Timothy Miller. Strongly recommended. Mike's maintaining supply chain examples where I'm looking at the consumer effects here. Mike's looking at replicating the SolarWinds style attacks, this time in Rust. And there is a screenshot from the demo. As I said, it was at Supply Chain Security Con last Monday and strongly recommended. So the fixes for this. First of all, what is signing? It is the mechanism by which we take some data, an asymmetric public and private key pair, and generate a signature. The public key can then validate that the signature was signed by that private key, and the signature itself might contain any sort of metadata about the original data. We then distribute this alongside the data that we're validating, and it gives our consumers a way to be sure that we, at that point in time, liked the person in control of the key, liked the thing enough to give it a stamp or a signature. And see Dan Lawrence's blog turn up a number of times across the next few slides. Okay, in Toto is a mechanism by which we can sign each individual build step. So we check out the code, we apply testing here probably happens in parallel. Maybe we're looking at our static analysis from an application perspective, our linting from a raw file perspective. Maybe we'll compile an artifact in there as well. Those parallel stages are complete. We build that and package it. Maybe the build is a separate step. In Toto doesn't care what is being verified. It just signs each individual build step if preconditions are met. And those preconditions look like this. Python is the kind of canonical example in a lot of their documentation. And here, the expected product, so the expected output that we as producers are going to send downstream is demo project foo.py. This is both a blessing and a curse because an overly restrictive set of constraints around the inputs or outputs become very difficult for a developer to manage. This layout file becomes a security boundary. Well, it is a security boundary. And so if the developer suddenly says, well, let's use a different name for the project or some different libraries, they have to then re-sign the layout, probably Segregation of duty in this case means that they don't have signing permission for the layout itself. So an overly restrictive layout is almost a road bump, a speed bump for developers. This is integrated into Tecton chains, and it's done in a looser version. So it just cares that the thing ran, as opposed to being restrictive and validating the inputs and outputs. So there are still compromises in the tooling at this point. Compromises is then different options that we can take rather than insecurities. So what else can we do? Once we've taken all those build stages and we have signed them individually, and we're happy that we validated the mechanisms that occurred, we have an artifact, and that's a container image, generally an OCI container image. We can go and sign all of those layers. Again, because of the Merkle tree effect in containers, same as Git, each layer contains a SHA, and then the final image is a superset of those things. So we only have to validate the top layer, but for correctness sake, we can certainly validate everything in between. And Sigstor is the emerging contender in this space. It has a few different components. Cosign is the signature generator, and it can actually sign a huge number of things in various different ways, but container signing is its bread and butter. Once we have those things signed, we then have a signature and no evidential place to leave it. So based upon the same certificate transparency logs that we see for things like, or sort of like the Let's Encrypt style, where each and every certificate issued goes into a public append-only ledger. Again, we're looking at hashing in order to make sure that we can't compromise, because in the same way that a blockchain or a Merkle tree or all these things work, by including the signature of the parent in the child, we can't tamper with any of those previous stages. So Recor is a tamper-proof transparency log for metadata and signatures. This is where we put the signatures that Cosign generates. So there is then a public record. Recor now operates as a public service, but of course it can run inside your organization's, hesitate to say perimeter, but it can run in your organization in order to provide that internal trust. Notary v1 was the canonical way of doing this. The project's probably 7 or so years old at this point, 6 or 7. Notary v2 is under development and will do the same kind of things as Cosign does, but probably suffers a little bit from first mover disadvantage in terms of already having a spec and some states. Cosign was released in March of this year. Cosign has multiple other bits in here. So first of all, we're looking at the full CO certificate authority. This means that we can essentially generate certificates. That also includes its own network time protocol implementation, because that's key. And we may as well, we could consume something else, but it kind of makes sense to bring that in because time is so important. So we can sign and publish the artifacts. Certificates, again, we can we can publish the signing certificates so that there's a public key record that we can use to validate the artifacts when we download them. And then there's also a key transparency log. Again, the goal here is just to make sure that we have an append-only ledger, so if something goes wrong, we can rewind time and figure out what was the nature of this compromise. Was there an issue with the protocol or the approach? And notably here, this entire game is about trusting people. Software does not compromise itself, is a quote that I stole from Mr. Mike Lieberman. Some companies don't want to give us any insight into how they're building or distributing. And there are cloud providers who lobby heavily in this space. It's highly suspect in my mind to not, by default, continue the open source mantra of openness and transparency. So what else do we have? I've spoken a lot about keys and signing. Of course, in order for those keys to be trusted, they have to come from a root of trust that we trust. Just like the public internet, we have our root certificate authorities. It would also be helpful if they were ephemeral, so they don't languish, and they, in terms of breach, are not that useful for longer than minutes or hours. Spiffy is a workload identity concept. It stands for Secure Production Infrastructure for Everybody. The product's a few years old at this stage. Excuse me. And it works on this principle of workload identity. That means taking metadata about a workload, that could be the node that it's on, the process identifier, and its command line invocation. Those are pretty sure that they'll stay uniquely identifying. An attestation tool, a privileged tool that can observe that metadata, then says, okay, I've identified this thing, it's unique, these are the attestation key and value pairs. Let's mint an X509 certificate with those things in. We then have the capacity to, for example, perform mutual TLS. This is how Istio works. It had the first implementation of Spiffy. The blast radius is such that if the node that we're on is compromised, we still run this risk. Excuse me. We still run this risk of malicious workloads being attested to. It's difficult to solve. It does limit the blast radius to just that one node, but it gives us a better default position than we'd be in if we were using long-lived keys. There is an integration in Toto that links Spiffy together. I hope to make it to the end of this presentation. Okay, into the final section, the software factory itself. Bertha is a British TV show from the 80s that for some reason spoke to me when writing this talk. The software factory is build pipelines for other pipelines. It's really complex. It requires a huge amount of front loading of effort. It requires exceptional DevOps implementation principles throughout the organization, and it's aggressive automation. There are multiple layers and approaches. We will just move on a little bit more quickly. So this is based upon the Department of Defense's reference pattern for a software factory that came out at the beginning of last year. The idea is we fix disaster recovery, we create ephemeral infrastructure, and we know that we've got everything provable and testable if we build other pipelines in an automated and repeatable way. The last pipeline is building software, and all the previous stages of the pipeline are building other pipelines or infrastructure, etc. The reference architecture here, if we look down in the bottom left, we see the identity attester. This is all important. This is the point of the system that hands out those workload identities. It's where we identify whether or not we trust these things by virtue of where they are and where they're running. And you can see in the middle, we have the CI/CD pipeline. And the metadata store at the top for publishing attestations is something like Recall. This is a more concrete implementation. There's work undergoing in the tag security, supply chain security working group to build this reference implementation. So what we have is Tekton, which is a CI/CD system built on Kubernetes for containers. The code goes in. We have Spire at the top, which authenticates the task run itself. It creates this SVID thing in the middle, a Spiffy verifiable identity. That is an X509 containing metadata about the workload. Once the task run, which is an individual build stage, completes, it generates its provenance, which is Tekton chains there, creating signatures. Again, it's observing in rather than being in process, and then it emits to Recall and a signature store. But what happens if this is compromised? We're in the same problem that we were with SolarWinds. So the trick is to run two, globally distributed, ideally, with a shared evidence lake in the middle. This means that in the event of compromise of one of those chains, one of those build pipelines rather, we can identify the disparity by virtue of the intermediate, by virtue of the testing that we can do, ensuring those logs, those signatures rather, are correct. I'm almost there. There is a white paper on the subject from Dan Lawrence, which is excellent. Thank you very much for your attention.